All right, screen share is coming up. It's actually the wrong one. Take this out. Tyler, are you doing research now?
Yeah, I work with scientists at LBL,
With who?
with Dr. Wakoskilid at LBL.
I don't, is him? I don't know him.
Yeah, he's not a member of our department. So
Yeah, right. So what does he do?
he works on carbon nanotubes, that kind of thing.
Oh, yeah. So what's new with carbon nanotubes?
In our group, we use them for biosensors, and we can actually get specific sensitivity in dirty solutions at like attomolar concentrations. So that's kind of what we've been working on recently.
What kind of sensors did you say?
Biomolecule sensors, like protein, stuff like
I see.
that.
I see. How big is a nanotube compared to the protein?
Well, the
Because
nanotubes are,
you could make a nanotube like one atom, down the core if you wanted to, right?
yeah, well, we use single walled nanotubes, but they're about, say, 100 microns tall, I think.
So what do you do with the biomolecule? I mean, what can you do besides suck it up in the tube, or is there something else?
We functionalize our nanotubes, and then the biomolecules kind of stick to it by like some chemical reaction or some interaction in some way.
Huh, I'll be darned. That's very interesting. So you're really doing kind of I mean, it's biophysics, right? But it's real physics too.
Yeah, in some sense, I guess. I'm just an undergrad, so I'll be going to grad school next semester or next year, I guess.
Oh yeah, that's great. That's great. Are you gonna do that kind of work in grad school?
Frankly, not too sure right now, but we'll see.
Where do you want to go to grad school?
Wherever I get in, right?
Yeah, well, what's your first choice?
Well, I'd love to go to Stanford just because I
Okay.
grew up in the Bay Area, so it'd be
Yeah,
nice.
Stanford's a great school. There's no doubt about it. I lived in Palo Alto ages ago. I never went to
Yeah,
Stanford, but I lived there.
a very
It's a
livable
nice place to
place.
live. I mean, of course, it's extremely expensive now because of Silicon Valley, but it's a nice place to live. It always was. I mean, going back decades into the past, 50 years ago, it was a great place to live.
Yeah, well, I guess we'll see how the dice rolls out, right?
Yeah. Actually, I hate to tell you this, but I was there 50 years ago, because I was there in 70, 71, 71, 72, 73.
It changed a lot since then.
Well, it's gotten much more, upper crust than it used to be. It was more a place where ordinary people lived, in those days. Of course, it still is, that way too, because there's people that have been there all the whole time. But if you're going to buy in right now, it's so expensive. You got to be quite wealthy. In those days, the poor people lived in Mountain View, or they lived in East Palo Alto. Okay, I'm going to get started because there's just a little bit of review here, not too much. So where we ended up last time was with an introduction to nuclear spins. And in particular, I was telling you about the rules that tell you which nuclear spins are allowed. So the notation we use is capital I. That's what I'll be using, capital I for the nuclear spin. That's an operator, of course. Its square is II plus 1 h bar squared, so that lowercase I is the quantum number, what we call the spin of the nucleus. The nucleus has, in general, has various multipole moments. The multipole moments are named by powers of 2 translated into Latin and Greek, and the corresponding power I'll call K. So monopole is K equals 0, dipole is K equals 1, and so on. And in general, we can call it a 2 to the K pole. Anyway, that's just terminology. So the rules about what multipoles of a nucleus are allowed is that odd K electric poles and even K magnetic poles are forbidden. And in the last lecture, I explained, at least in the case of the electric dipole, that the reason they're forbidden is because they violate both parity and time reversal. And this of course leaves open the question about what about small effects that violate parity and time reversal, and I discussed some of that in the last lecture. You can read more about it in the notes. There's the issue of the so-called strong CP problem, which arises here. But in any case, this at least explains why it is that if they're non-zero, they're certainly very small. In fact, they've not been measured yet. The second rule regarding the allowed multipole moments is that K, which is not only the index of the multipole, but it's also the order of the irreducible tensor operator, which is represented by the corresponding multipole, that has to be less than or equal to twice the spin of the nucleus. And I'm not going to elaborate this very much because that was actually the content of a homework problem a couple of weeks ago. So I hope you remember that. But this is just based on the fact that in the Hilbert space for the nucleus of spin I, the maximum rank of an irreducible tensor operator is twice I. All right. So anyway, that's kind of an introduction into the rules that apply to allowed multiple moments. Let me now run through some examples just to show you how this works out in practice. Let's see, turn this around. So for example, if we take the case of the proton, which of course is the nucleus of ordinary hydrogen, proton has spin I equals 1/2. And so two I's, so that means that K has got to be less than or equal to 1. And so what that means is that for the proton is allowed to have a K equals 0, the electric monopole is allowed. K equals 1 would be the magnetic dipole, that's allowed, but nothing beyond that. Well, in fact, the proton does have an electric monopole moment, and it does have a magnetic dipole moment. We know about that from earlier work on magnetic moments and spin, but it does not have a quadrupole moment. That's rigorously true, it's just 0. By the way, this also applies to the neutron because the neutron also has spin 1/2. It's the same thing. On the other hand, to go to the next most complicated nucleus, the first nucleus that has any complexity at all is the deuteron. Deuteron has a spin of 1. There's no way to know that. It's an experimental fact, but you could narrow the possibilities down by adding angular momenta. The most likely results would be either 0 or 1, combining two spin 1/2 particles, a proton and neutron. But in fact, the deuteron has spin equal to 1. So that means it's allowed to have not only the electric monopole moment, which of course it does have, also a magnetic dipole moment, which it also has, but it's also allowed to have an electric quadrupole moment. And now the question then arises, does it have an electric quadrupole moment? Really, in other words, in the real world? And the answer is yes, indeed, it does. The deuteron does have an electric quadrupole moment, as it was observed experimentally by Rabi in the 1930s with his beam techniques. And it's a fact that it's an experimental fact. When you measure the magnitude of the electric quadrupole moment, it gives you information about the wave function of the of the proton and the neutron, which are orbiting one another inside that nucleus. The deuteron is like the hydrogen atom of nuclear physics, is the simplest possible nucleus. If we take the case of the alpha particle, which is of course the helium-4 nucleus, that has I equals 0, it's a spinless particle. And so that means that it has an electric monopole moment, that's the charge, and nothing else. There is no magnetic dipole, nothing else beyond that. Therefore, ordinary helium doesn't have any hyperfine effects at all. Hyperfine effects are defined as the interaction between the higher order multipole moments of the nucleus and the dynamics of the electron, but those are absent for the case of helium-4. All right, so those are just some examples of the application of these rules. The problem that I want to address tonight in tonight's lecture is that of hyperfine effects which are due to a magnetic dipole moment. This would apply in ordinary hydrogen with a proton as a nucleus, and in many other atoms as well. Depending on the nucleus, there may also be higher order moments, but I'm going to ignore them because that just complicates the presentation. So we're going to take into effect the simplest possible case of hyperfine effects, which is that of the interaction of the magnetic moment of the nucleus and the atomic electron. The idea is the nucleus creates a dipole moment. The nucleus has a dipole moment, creates a dipole magnetic field, and the electron in its orbit around the nucleus feels the magnetic field and responds to it. By the way, the nucleus also responds. It precesses in the magnetic field that it sees, which is due to the electron. So there's a coupling between the electronic degrees of freedom and the nuclear degrees of freedom. So that's the physical system that we want to analyze tonight. So I'd like to begin by saying some things about magnetic dipoles. At first, I'll be just telling you stuff that comes straight out of a standard magnetostatics chapter in a book like Griffiths or Jackson. If you have a point dipole with a magnetic moment mu, then the vector potential produced by that is A of R, let's write it like this way, is mu cross R divided by R cubed. You can look this up in the books. This is what would apply for a point dipole. Point dipole is kind of an idealization. It's one in which the current that produces the magnetic field is concentrated into a smaller and smaller region of space. The magnitude of the current goes to infinity, whereas the volume of the current goes to zero, in such a way as to create this vector potential outside the current distribution. Point dipole is a idealization in which that is carried to its limit. You have kind of delta function like singularities of the current down at the origin. This is kind of a generalization of a charged particle with a Coulomb point particle with a Coulomb potential, because there again you have a singularity at the origin. So the vector potential for a point dipole is rather singular at the origin. It goes like 1 over R squared if you count the factor of R in the numerator. If you compute the magnetic field from this, which I won't bother to write down right now, we'll look at it a little bit later. It's also, in fact, it's even more singular than A is. These singularities in the vector potential in the magnetic field give rise to technical difficulties in doing the quantum mechanics at a later stage of this calculation. You end up with integrals that are not defined. The same thing happens with the Coulomb potential, by the way. If you look at enough problems, we actually saw that in the hyperfine effects. A spin orbit correction required us to compute the expectation value of 1 over R cubed, and that is actually not defined for states with L equals 0. And you'll find similar things to that for these fields as well. So we're going to deal with this problem, the singularity, by in effect smoothing out the point dipole over a finite volume and adopt a model for the currents that produce the magnetic fields. We'll take the case of a uniformly magnetized sphere. So we'll smooth out the point dipole over the region of the sphere. Let's give the sphere a radius, which we'll call A, like this, and we'll give it a uniform magnetization inside the sphere. Now the magnetization I'll denote by capital M. Magnetization is defined as the dipole moment per unit volume. So the dipole moment we want for our sphere is given by the magnetic moment, the net magnetic moment that we really want the field to have, divided by the volume of the sphere. The volume of the sphere, of course, is 4/3 pi A cubed. So this is what we want. So this is a problem then of the magnetic field produced by a uniformly magnetized sphere. As I say, this is a standard problem in magnetostatics. We can solve it in the following way. To be general, let's suppose we have now an arbitrary distribution of magnetization with some coordinate system X, Y, and Z. And let's take some small volume element here inside this distribution. Let's suppose this so let's draw the vector there to it and call it R prime. I'll use the prime to indicate a vector that runs over the source distribution. We want to measure the fields at some field point, which I'll call R, which may or may not be inside, maybe inside or outside the distribution. I'm drawing it here as if it's outside. So we'd like to find the field at R. So the field at RA, evaluated at R, is going to be a contribution coming from, it's going to come from some contributions. One of them is to take the magnetization vector at the location R prime multiply it by the volume element d cubed r prime like this. I'll leave some space in here. The product of these two is equal to the net magnetic moment of that little volume element. And that's going to contribute to the vector potential at the observation point, the quantity, which is m of r prime, crossed into r minus r prime vector divided by that vector cubed, r minus r prime cubed. And what I've got written down here so far is really just a version of the point dipole formula written above, except mu has been replaced by m times d cubed r, the infinitesimal contribution to the magnetic moment, and r vector has been replaced by r minus r prime because we shifted the origin. That's really all it is. In any case, if we then integrate this over the region of the source, this is a d cubed r, then what we get is the net vector potential at the field point. So this is just straightforward stuff. Now, for our problem, the region is not some lumpy region. Our problem, it's going to be a sphere. We'll center the sphere at the center of the origin. So we want to integrate, for our problem, we want to integrate over magnitude r prime is less than or equal to the radius a. This just means integrating over the sphere. And also for our problem, magnetization is actually constant, so we can bring it out of the integral. Moreover, the magnetization is indicated above as mu divided by the volume. So I can write this way as equal to mu magnetic moment divided by the volume v, crossed into the integral, which I'll write out as d cubed r prime, and then just writing it out explicitly, r minus r prime divided by the cube of that same vector, r prime cubed. Okay, running out of space here. So so if you can see that, that's the integral we need to evaluate. Now, this integral, which is left over here, if you look at it enough, you can see what this is that this is actually has an interpretation in electrostatics. This again is taken over the region of a sphere where r prime is less than or equal to a, the radius of the sphere. This is an interpretation in electrostatics. This is the electric field produced by a charge distribution inside the sphere of radius a, a uniform charge distribution. In fact, charge density is equal to 1 inside this formula, like this. And otherwise, this integral is the electric field produced at field point r due to the charge distribution. That field point r could be either inside or outside of the sphere. The formula works in either case. But the point is that electric field can be evaluated by Gauss's law. It's easy to do. This is just equal to the r hat divided by r squared, which is what you get from Coulomb's law for an electric field, multiplied by what I'll call Q of r, which is the total charge inside radius r. And Q of r in turn, it's easy to see what that is. It's equal to 4/3 pi r cubed if r is less than or equal to the radius of the sphere. And it's equal to 4/3 pi a cubed if r is greater than or equal to the radius of the sphere. Because in the latter case, your observation point is outside the sphere, so you got the whole charge. We can write this also in terms of the volume as being the volume is 4/3 pi a cubed, so the upper formula becomes r cubed divided by a cubed. No, let me see. Let me do it right. No, I want to do this right. So the upper formula becomes the volume v times r cubed divided by a cubed. And the lower formula is just the volume v. So this is in the two cases, r is less than or equal to a, or r is greater than or equal to a, like so. All right. Now then, we can kind of combine this stuff together then. We've got the volume factor up here, which will cancel out these volume factors here. We've got an r hat over r squared, but let's rewrite that as r vector over r cubed. And then we can bring this r cubed here inside, and it'll cancel out that r cubed there and divide this one by r cubed, like so. And if we put the pieces together, then what we get is the formula for a of r. And it's going to be equal to the magnetic moment mu crossed into the vector r, multiplied times 1 over a cubed if r is less than or equal to the radius a, and 1 over r cubed if r is greater than or equal to the radius a. And this then turns into the expression for the vector potential produced by a uniformly magnetized sphere. You've probably seen this before in your undergraduate E&M course. And I know it's in Griffiths. It's in Jackson too. Okay. Now then, let me put some stuff here where I need it. One of the things you may notice from this formula is that if you take the exterior solution, is you've got mu cross r over r cubed, and that's the same thing as the field of a point dipole. So what this means is that if you're outside the uniformly magnetized sphere, you can't tell from the magnetic field alone whether you've got a point dipole or whether some distribution over a sphere. Or you can't tell what the radius, even if you knew it was a sphere, you can't tell what the radius is. This is obviously like the gravitational problem, where if you're outside a spherically symmetric distribution of mass, and all you have for sampling it is the gravitational field, you can tell what the total mass is, but you cannot tell what its radial distribution is, as long as you're outside that distribution. So this is obviously a magnetic generalization of that. On the other hand, if you're inside the sphere, you have a different formula. And in particular, the vector potential does not diverge. It's finite and well behaved. That's the purpose of doing this, making this model of the uniform sphere. If we take the curl of this to get the magnetic field, then what we find is this, is the magnetic field is equal to, I can write it this way, is it's equal to the two cases. It's twice the magnetic moment mu divided by a cubed if r is less than or equal to a. And it's equal to mu dotted into a certain tensor t, which I'll explain this notation in a minute, if r is greater than or equal to a. The notation is this tensor t has components tij is given by 3 xij minus delta ij r squared. This is the same tensor we've been seeing appearing in the analysis of multipole moments. It occurs in the electric quadrupole moment, and we see here that it appears also in the magnetic field for a magnetic dipole moment. This mu dotted into b, what that means is that's a vector, mu dotted into t. That's a vector given by sort of thinking of mu as a row vector and t as a matrix. Anyway, so the ith component of this is the same thing as the sum on j of mu sub j times tji. You can see it's just left multiplying by mu. That's all the notation means. But anyway, with that notation and those understandings, this gives us the magnetic field. One of the things you can see from this is the magnetic field inside the sphere is actually uniform. I'm sure you've seen these pictures. It looks like this. Is the magnetic field lines inside the sphere look like this, and then outside they kind of do this. They loop around to give you the dipole field, you see, but they give you finite lines inside. So this is what it looks like. So having done this, having smeared out our point dipole over a sphere, we're now guaranteed that the integrals that we encounter in quantum mechanics will be convergent. There will be no divergences from the integrals. All right, so that's the uniformly magnetized sphere. Let's see, it's convenient to write these formulas so I don't have to present cases. Allow me to do this by introducing some functions. Let me make some definitions. Let me define a function delta of r is equal to 1 over a cubed in the inner region, r less than or equal to a, and 0 in the outer region. And then I'll define another function I'll call f of r, which is equal to 0 in the inner region, and it's equal to 1 in the outer region. So these are non-zero and complementary regions, you see. And with that notation, I can combine these formulas together. Let me see if I have space to do it here. So the vector potential then becomes A of R, can be written this way. Can be written as equal to mu cross R times delta of R. That's this 1 over a cubed here, plus f of r divided by r cubed for the outer part. And likewise, the magnetic field B of r can be written this way as the magnetic moment vector mu dotted into twice the identity tensor, which I'll write this way with a double arrow over it, times delta of r, plus f of r. I see I made a mistake up here. This is not t, this is t divided by r to the 5th power. This becomes f of r divided by r to the 5th times the tensor t. And so the mu dotted into the identity just gives me mu. And the mu dotted into t gives me the mu dot t that I see up there. Here's the mu and here's the factor of 2. So this is just another way of writing this. It's a little more compact using these two functions. Okay. In the limit at which a goes to 0, which we're eventually going to want to take, you see these two terms cover different regions of space. Ultimately, the first term shrinks down to what's happening right at the origin. Okay, now then. By the way, the mu that appears here, before I'm done with this, the mu that appears here is, of course, the magnetic moment of the nucleus. That's the application we have here. And the magnetic moment of the nucleus, we know about that. That's equal to the nuclear G factor, I'll call G sub n, times the nuclear magnetic moment, mu sub n, times the nuclear spin I divided by h bar. Now, I'm actually going to be using atomic units in a minute, so the h bars will go away. But this is hopefully a familiar formula to you for nuclear spins back when we were doing spins in magnetic fields. Okay, so our atomic electron is moving in the magnetic field given by the A and the B that I've just written down here, which in turn comes from the nucleus. So let's write down the Hamiltonian for the electron in that magnetic field. It's going to be 1 over 2m p, and it's plus E over c times the vector potential A squared. There's a central force potential V of r, which is Coulomb if you want. We'll actually specialize to hydrogen in a minute. And then I'm going to add to this as well the fine structure terms, and I'm even going to add a term for the Lamb shift, which I'll explain in a minute. And then we have minus the mu dot b for the interaction of the electron spin with the magnetic field. Now this mu is the electron mu, so I'll put an E subscript on it to make it clear that it's not the same as that mu, which is the mu of the nucleus. All right. If we go over to atomic units, then there's things that simplify here. The minus mu E dot b turns into plus alpha times the spin dotted into b. We saw that in the Zeeman effect. The E over c turns into just the fine structure constant alpha. The m goes away. In atomic units, it's 1. So I can write the Hamiltonian this way. If I expand out the kinetic energy, it becomes p squared over 2. And then I get plus alpha times p dotted into the vector potential A. We get another term, which is alpha squared A squared over 2. These three terms are the expansion of the kinetic energy. Then copying the true potential, the fine structure term, and the Lamb shift, the Lamb Hamiltonian, I'll copy that. And the last term I'll just copy as plus alpha times S dotted into B. Now, this Hamiltonian could be the Hamiltonian for the Zeeman effect. And it would be, in fact, if we put in B and A, the external field that you would have for the Zeeman effect. In this problem, however, the B and the A are not external fields. They're coming from the nucleus and they're given by these more complicated formulas up above. They're certainly not uniform. So you basically want to take this A and the B then and plug it into here. Now, the magnetic fields that are produced by the spin of the nucleus are quite weak. You can do the actual numbers, but the analysis works very much as in the case of the Zeeman effect, and it shows us that the P dot A term here is much smaller than the P squared term. And then likewise, the quadratic term is much smaller still. So we can neglect the A squared term in comparison to the P dot A. On the other hand, the P dot A is comparable to the S dot B, and those two terms taken together, well, they were what we called H Zeeman when we were doing the Zeeman effect. That was the perturbing Hamiltonian. It's also the perturbing Hamiltonian in this case as well, except A and B are now different. So we can write this as an H0, which I'll just pull it together here as P squared over 2 plus V of R plus H fine structure plus H Lamb, which is basically has all the physics in it that we looked at when we were working on fine structure, including the Lamb shift. And the rest of it, the H1 is fine structure constant alpha times P dot A plus S dot B. And as we see, and this is our perturbation, and as we see, it has an orbital part and it has a spin part is a contribution to the two contributions to the perturbing Hamiltonian H1. So this gives us an unperturbed Hamiltonian and a perturbation problem to work on now. All right, now before we jump into that, I should say some things about the unperturbed system. The unperturbed system. Let's see. Maybe before I do that, let's work on putting H1 into a more explicit form using the explicit formulas for the A and the B, which I have up above. Let me do that calculation first. So as I say, there's an orbital in the spin part. The orbital part is alpha times P dot A. So let's look at A. It's got the mu cross R in there, but the mu is given in terms of the nuclear spin I the G factors and nuclear magnetic moment. So in multiplying things together, I'm going to get the fine structure constant alpha here. Just look at the constants first. I've got alpha here. I've got G and mu in there. Those are the constants. The H bar will go away because we're using atomic units. The Bohr magneton in ordinary Gaussian units anyways is EH bar over 2 MC. And if you put this into atomic units, then it just turns into, since C is equal to 1 over alpha and the H bar and M go away, it just turns into alpha over 2. And so the electron G factor times mu sub B is actually equal to alpha if we approximate G equals 2, which is a good approximation. So multiplying this alpha times that G and G mu n gives us an overall constant that I'm going to define to be K. It's the electron G factor times the Bohr magneton times the nuclear G factor times the nuclear magneton. And this K then is a measure of the interaction of the magnetic moments coming from the nucleus with that of the electron. And that's going to be a common constant factor out front. Now then, taking the constants out, the mu cross R is going to turn into an I cross R, spin crossed into R. But that's going to get multiplied by P because we have P dot A. So we're going to get something that looks like this. We can get P dotted into I crossed with R. By rearranging the triple product, that's I dotted into R cross P, which is the orbital angular momentum. So we get I dotted into L. And the result of this, putting this together then, if I can make some room here then, is that H1 orbital looks like this. It's equal to the constant K times I dotted into L times this other factor up above, which I'll just copy, the delta of R plus F of R divided by R cubed. Like so. All right. Now then, what about the spin part of the Hamiltonian? That's S dot B with an alpha here. The alpha and the constants from the G and mu n will combine together to give us a factor of K just like before. I think that's disappeared now. Let's see, let me make sure I've got this on the screen here. For the S dot B term, let's look at the B here. The B has got this mu multiplied onto this tensor. So S dot B, we'll put the S on the right. It's going to give us a mu on the left and a dotted tensor in the middle and the spin, electron spin S on the right. The constants will combine together to give us this K factor here. The mu otherwise will get replaced by the nuclear spin I. So we can get I, nuclear spin I on the left, and electron spin on the left multiplied onto this tensor. And the result is that the H1 spin is equal to the same factor K. It's got I on the left dotted into this tensor, which is where am I here? It's twice the identity tensor times delta of R plus F of R divided by R to the fifth times this tensor capital T dotted into the spin S on the right. Okay. And here then is a Hamiltonian, the perturbing Hamiltonians written out explicitly in terms of the operators that we're interested in. All right, quantum operators. All right, now, so the unperturbed Hamiltonian is basically the Hamiltonian that we had in studying fine structure, adding in the small corrections like the Lamb shift and so on. So we know about its energy eigenstates and so on. The perturbing Hamiltonian, however, involves a new degree of freedom, which is namely the nuclear degree of freedom. It explicitly depends on the nuclear spin I. So what this means is by including this perturbation or its interaction with the atomic nucleus, no surprise, the Hilbert space enlarges because it has to include the nuclear degrees of freedom. So we have a new Hilbert space, let me call it E total. And this is equal to the electronic Hilbert space, which is what we saw in the fine structure, tensor product with a nuclear Hilbert space for the nucleus. And if we want a basis in this space, it's equal to the product of a basis in the electronic Hilbert space. Well, for that, we might as well take the eigenbasis of H0. And that's in the quantum numbers we've used for fine structure. That's NLJ and MJ, corresponding to operators H0, H0, L squared, J squared, and J sub Z, multiplied times the basis in the nuclear Hilbert space, which is I and M sub I, where I is the nuclear spin and M sub I is the magnetic quantum number of the nucleus, which for the proton would just be plus and minus a half. as would the number I. We'll abbreviate this product basis in the following form as NLJ M sub j M sub I, and I'll give it a name. I'll call it the uncoupled basis. This is not the same uncoupled basis we had before. In fact, it's really kind of a partially coupled basis because L and orbital and spin, L and S, have been combined together to make J. But what has not happened now is we have not yet coupled together J with I, so it's uncoupled insofar as the J and I are concerned. We'll address that later. But anyway, this is a basis for the combined Hilbert space. And so what this means is that our energy shifts using the rules for degenerate perturbation theory. Let me tear this off and move it up a little bit. The energy shifts are given by the eigenvalues of a matrix, and we put down the unperturbed eigenstates, which are NLJ M sub j M sub I. We sandwich them around the perturbation H1. We have NLJ M sub j and M sub I on the other side. And now we're not done yet because we need to look at the indices. The energy levels, to go back up above, the energy levels of the unperturbed Hamiltonian, if we ignored the Lamb shift, it would just be the fine structure energy levels, which depend only on the two quantum numbers N and L, the principal quantum number, N and J. It's independent of the quantum number L. But including the Lamb shift breaks the L degeneracy. Remember, it lifts the 2s a half state above the 2p a half state. So the energy levels have the form of NLJ. I should tell you why I'm including the Lamb shift here. It doesn't complicate the analysis much at all, but the reason that we're including it is because, in fact, the hyperfine effects are smaller than that of the Lamb shift. And so it would be unrealistic to try to ignore the Lamb shift. It would be, and I want to do a realistic treatment of the fine structure. That's the reason for doing it, to make it an honest and realistic calculation. But the main effect of the Lamb shift on this analysis is just simply to make us notice that the energy levels depend on L now, as well as the other two quantum numbers. Therefore, going back to our perturbation problem here, the NLJ quantum numbers on the two sides are the labels of the unperturbed energy eigenstates, which are degenerate, whereas the MJ and MI quantum numbers, which appear on the two sides, are the labels of the basis vectors inside the degenerate eigenspace. And for that reason, we ought to put primes on the MI and MJ on the other sides because they're not required to be the same. And in fact, what you see is you get a matrix that has dimension 2j plus 1 times 2i plus 1 that needs to be diagonalized if you wanted to find the energy shifts using this representation. Okay, hope that's clear. Let me pause and just ask if there's any questions about this so far. I'm trying to use.
I'm wondering, we used the first order perturbed wave functions for the fine structure to do first order perturbation for hyperfine. So is it possible that the second order effects of fine structure are comparable in energy to first order hyperfine?
Yeah, so that's good thinking. So the wave functions that we used, when you do degenerate perturbation theory, the simplest calculation and the most common one in practice is one where the wave function you end up with are actually unperturbed wave functions. They're only 0th order wave functions. However, they differ from the case of the unperturbed system because in the unperturbed system, they were all degenerate and you couldn't say which one was which. I mean, you could, but they were not distinguished by their energy. Whereas when you turn the perturbation on, they do become distinguished by their energy. And now you know which one of those inside the degenerate eigenspace corresponds to a given perturbed energy. So if you like, what we're really doing is working with 0th order wave functions. Do you follow me?
But we also chose a basis in which the first order wave function correction is 0, right?
No.
I mean, because the matrix is diagonal.
No, we just never evaluated the first order correction to the wave function.
Oh, okay.
One could if one wanted to, but we didn't do it. This is good enough. This is just the 0th order. So
okay.
to 0th order, these are the energy eigenfunctions of the perturbed system. In this case, the fine structure system. And so we're going to use them as basis functions for the analysis of the smaller perturbation, the hyperfine effects which are imposed on this.
But if the if the H1 matrix in the hyperfine first order hyperfine correction, if that matrix is diagonal, then doesn't that mean
But it's not diagonal.
like in the coupled basis, it's
Well, you mean, and this is what I'm calling here the uncoupled basis. This is not diagonal. That's going to be my next point. Is that you can't drop these primes here.
oh, I meant for the fine structure correction when we did that.
Yes. Then they were diagonal because we went to what we call the coupled basis there. It's not the same as what I'm talking about tonight.
Right. So doesn't that mean that that for the fine structure correction, if the H1 matrix is diagonal, then that means that that the zeroth order wave functions are also eigenfunctions?
No, because there are first order corrections to the wave functions. Go back to the formalism of perturbation theory and you'll see that. In the case of degenerate perturbation theory, we just stopped at the zeroth order wave function and didn't go to the first order correction because in fact, we don't need it for most applications.
Okay.
But if you want to find it, you can find it. You'll see there's a way of doing it.
Okay.
This is actually good enough for most of what you want to do. All right.
Okay. And actually going back to my original question,
so one could say that these wave functions that I'm using here are the real energy eigenfunctions in the of this H0 up above, including the fine structure and Lamb shift, to within corrections which are of the order of magnitude, relative order of magnitude of the fine structure corrections. 1 10 to the minus 4 in the case of hydrogen. They're pretty good wave functions, you see.
okay. I see.
All right, now, so, but the point is,
question too, actually.
Yes.
I was wondering, are A and B, are they both pseudo vectors?
B is a pseudovector, yes. Magnetic field is a pseudovector.
Or is A a true vector?
A is a true vector.
No question, but
Yeah,
okay.
because the curl kind of flips the vector pseudovector.
Okay.
Yeah.
Okay, thank you.
Yeah, good. Actually, it's slightly more tricky than that. It depends on whether you're talking about classical vector analysis or quantum, whether it's an external field and so on. But basically, the basic idea is that every cross product introduced flips something from a pseudo to a true and vice versa, including the curl as a kind of a cross product.
Thank you.
All right. Now, this matrix is not diagonal, and the reason is because the operators that corresponding to the quantum numbers mj and mi are, of course, jz and j and iz. That's what they are, and they're components of the vectors j vector and I vector. And these j vector and I vector do not commute with h1. It's easy enough to see that just by looking at this I dot L expression here. This is a dot product between a nuclear spin and an electronic angular momentum. So a vector from one type of degree of freedom and a vector from another. So the J vector is the total electronic angular momentum. So it generates electronic rotations, and it will rotate the L half of this dot product, but not the I half. So the I dot L is not invariant, it's not a scalar under J. Nor does it scalar under I, because I will generate rotations of the I part, but not the L part. And so therefore, this thing is not diagonal in these two indices, MJ and MI, and you really would need the primes. So that means you'd have to diagonalize a matrix of that size to carry out this perturbation calculation. And clearly we don't want to do that. So how do we solve this problem? Well, I hope the solution is obvious. It is that we just go to a coupled basis, a new coupled basis, in which we now couple together the J and the I. So this is to say we want to look at the sum angular momentum J plus I. And in the atomic physics business, they give this a name F. They call it F as a total angular momentum. This is the same thing as L plus S plus I. So it's really the sum of three angular momenta you see in the atom: the orbital angular momentum of the electron, the spin of the electron, and the spin of the nucleus. Nucleus doesn't have an orbital angular momentum of its own because it's, we're using effectively infinitely massive approximation here, so it's not moving. But anyway, this is the sum of the three angular momenta which appear. All right. And so if we do this, then what we want to do is to transform from the former set of good quantum numbers that included JZ and IZ, and go over to the new ones in which the good quantum numbers are F squared and F sub Z. And so for that, we need a Clebsch-Gordon expansion. It's going to look like this. We'll have vectors we'll call NLJ, F, and M sub F. And the CSCO, complete set of commuting observables here, the N corresponds to H naught, the L is L squared, the J is J squared, the F is F squared, and the M sub J is F sub Z. This is going to be our complete set of 1, 2, 3, 4, 5. And I left off the I squared and S squared because those are constant. You add them and you'd have 7. In any case, this is given by the sum on magnetic quantum numbers Mi and Mj of the uncoupled basis vector NLJ, M sub J, M sub I times the Clebsch-Gordon coefficient, which is involved in adding J plus I. It's Ji, Mj, Mi, scalar product with FMF, like so. And so this is just straightforward, adding two angular momenta to create a third. But now if we do the perturbation problem in this basis, we have, and lest I run off the page, we have N, L, J, F, M sub F, now sandwiched around H1, N, L, J, F, and M sub F. And now, again, let's analyze the indices. The NLJ, as before, indicates the unperturbed energy level, and the F and M sub F indicate the basis vector inside the degenerate eigenspace on both sides. The operators that correspond to those quantum numbers are F squared and F sub Z. Now, in fact, the total F sub Z is a component of the vector F. Let's look at the whole vector. The whole vector F commutes with H1. You'll remember the term we were looking at was I dotted into L. I dotted into L is actually a scalar under rotations generated by F, because F rotates the entire system, not just the electronic degrees of freedom, but also the nuclear ones. So both I and L are rotated by the same rotation, and so the dot product is invariant. This is a line of logic we've used before in a different context and carries over here. So what that means is we don't need primes in the F and M sub F, and therefore the energy shifts are just given by the diagonal matrix elements in this basis, and so we can just write delta E is equal to that. So in effect, once again, we have reduced degenerate perturbation theory to non-degenerate perturbation theory. You just need to do an expectation value in order to get the energy shift, and that's how it works out. So I think the vast majority of problems that we do in this course are going to be like that. We escape having to diagonalize matrices. I think in the Stark effect, we did diagonalize a 2x2 matrix. All right, excuse me. All right, so this is what we need to evaluate. Now, let's go back a page or two here and look at the perturbing Hamiltonian. Here it is in its orbital and spin parts. I'd like to analyze this a little further by taking the limit as the radius of our sphere goes to 0 as to what happens to these functions delta of R and F of R. So let's talk about that and see what this does to these things. So that's a little bit of a digression then, and then we'll come back to the perturbation problem. So delta of R, let's look at the limit of this as A goes to 0, size of the sphere goes to 0. Delta of R, I'll remind you, is 1 over A cubed when R was less than or equal to A, and it's 0 outside that. That means that the integral over all space d cubed R of delta of R is just equal to the volume times 1 over A cubed, but the volume is 4/3 pi A cubed, so it just turns into 4/3 pi. So as A goes to 0, this is a function which is concentrated into an ever smaller region of space, and whose value keeps getting bigger and bigger as the region shrinks, in such a way that the total integral of the function is a constant. And that means that this limit is 4 pi over 3 times the delta function, delta cubed R. On the other hand, the limit as A goes to 0 of the function F of R. F of R was just a 1 in the exterior region and 0 in the interior region. So if the interior region shrinks to nothing, then you just have a 1. So that's a trivial limit. So if I put them in here, and here's my formulas for H1 orbital, H1 spin, and put them in, then I can do something with these deltas and these Fs and replace them by what we want. Allow me to do that. I hope I can get this all on the same page here. So then what we'll get is this is H1 orbital would be equal to our constant K times I dotted into L. And then we have 4 pi over 3 times Dirac delta function of R at the origin. And then the second term becomes 1 over R cubed. And then H1 spin is equal to K. For the first term, I'm going to take the I and the S sandwiched on the identity and just bring them in. I get K, it'll look like this. It'll be 8 pi over 3 times the nuclear spin dotted into the electronic spin times delta cubed R. And then we get plus 1 over R to the 5th times the electronic times the nuclear spin on the left, the tensor T in the middle, and then the electronic spin on the right like this. And this then becomes our formulas for the orbital and spin contributions. Now, actually, I'm kind of breaking the rules that I set up earlier because I said we smooth the singularity outs of the integrals. We could do the integrals and then get finite answers. And the idea is you do the integral with a finite sphere of finite radius, and then you take the limit as a goes to 0. What I'm doing here is I'm taking the limit first, and then later we'll do the integrals. And I'm doing it because it works out that way, and this is easier to do. But if you to be technical about it, you really should do it in the reverse order. In any case, we'll notice that we get these delta function contributions here. These delta function contributions are called contact terms, is the name for them, because they vanish unless the electron is in contact with the nucleus. That is to say, when the R vector is equal to 0. In fact, they're oftentimes called the Fermi contact terms. Fermi, if I can spell his name right, because Fermi first did this analysis of hyperfine effects in the early 1930s. This is really Fermi's calculation I'm presenting to you tonight, so that's why they're called that. So you can see that there are two contributions to H1. There's these Fermi contact terms, and then there's the other terms. The Fermi contact terms are going to only be active for states for which the angular momentum L is equal to 0, because we know that the wave function is 0 at the origin unless L is equal to 0. If L is equal to 0, the wave function is constant. Remember, the wave function goes like R to the L near the origin for central force problems. So the contact terms are going to vanish if L is not equal to 0. So to simplify our calculation, let's take what we'll call case 1, which will be the case where L is not equal to 0. Because if that's so, then we can just ignore the Fermi contact terms and we just have the final two terms. That's all that we have. In that case, we have an H1 effective. An H1 effective is the same as H1, but dropping the Fermi contact terms. And you can see it's got a common factor of K out front. The constant K is the same. And otherwise, it's got a constant factor of the spin, angular momentum I on the left, dotted into a vector. Here it's I dotted into this thing. So let me write it as K times I dotted into a vector I'll call G, where G is defined as the, from the orbital part, it's going to be L vector divided by R cubed, like that. And for the spin part, it's going to be plus the tensor T dotted into the spin vector S divided by R to the 5th. So this is a separation of H1 into a nuclear part I and in a vector G, which is a purely electronic operator, as you can see here, like this. All right. And so now what we need to do then is to evaluate diagonal elements only we need of the matrix element N, L, J, F, M sub F, sandwiched around. I'll take the K out. This will be the delta E will be equal to this. Taking the K out, what's left in the middle is I dotted into G. And then the same thing on the right-hand side, N, L, J, F, M sub F. This is what we want. All right. This operator I dot G is a scalar operator under the total rotations of the entire system, which are generated by the vector F. And what that means is, if you use the Wigner-Eckhart theorem, it means that this matrix element is going to be diagonal. We know it's diagonal in M sub F anyway, because the operator commutes with F sub Z. But the Wigner-Eckhart theorem tells us more than that. It tells us the answer is actually independent of MF. This is the usual situation in systems with rotational invariance, is that if they're isolated, is that the energy levels don't depend on the magnetic quantum number of the total angular momentum. In this case, the total angular momentum is F. It includes the nuclear spin as well. And these energy levels don't depend on M sub F. So this is just following this rule that we worked out earlier in discussions of rotational invariance and its effect on energy levels. All right, but now we need to actually evaluate it. We're going to evaluate it by making the following observation, is that this is using some tricks now, is that the J values on the two sides here are the same. On the other hand, the G is a purely electronic operator, of which J is the total angular momentum. So we get to use the projection theorem for the matrix elements of a vector operator. And the projection theorem really amounts to just taking the vector G, and in this case, replacing it by its projection onto the vector J. So it gets replaced by J times J dotted into G, divided by the square of J, which is J times J plus a half. So it's allowed then to take this projection and to put it into that operator in the middle of the matrix element, and the answers won't change. Let's work on this J dot G, which occurs here. There's some algebra in this J dot G, which comes from here. Let's work on this. So the J is L plus S, and the G, which I'll copy, is L divided by R cubed, plus the tensor T dotted into S over R to the fifth. I'll write that out explicitly. That becomes 3R times R dotted into S minus R squared times S divided by R to the fifth. All right. So we need to just work this out. Let's analyze that. So this is straightforward algebra. So multiplying the L dot S onto the first term, I get L squared over R cubed plus L dot S over R cubed. That takes care of the L dot S times the first term. As far as the second term is concerned, let's first multiply it by L. L dotted into R is 0, because L is R cross P, and the triple product has now got two vectors being the same. L dotted into R is 0, so that goes out. As far as the second term goes, comes in with a minus sign. We get an R squared, we get L dot S, and this is divided by R to the fifth. So that takes care of the L part, multiplying the second term. Now then, let's do the spin part, multiplying the second term. We're going to get a 3. Spin is going to give us an R dot S quantity squared. Then we get minus R squared times S squared, and that's divided by R to the fifth. Okay, so that's the multiplying this out. We've got these 4 terms. Now you can see that this term with L dot S and that one with L dot S cancel each other. So good, it simplifies. What about the last term here? Let's look at the R dot S squared. Let's evaluate this. S is equal to sigma over 2, the Pauli matrices, sigma over 2. So R dot S squared is given by 1/4 of R dot sigma squared. And that's equal to 1/4 if I write it out in index notation of xi xj times sigma I sigma j. But that's the same thing as 1/4 of xi xj using the algebra of Pauli matrices. It's delta ij plus I epsilon ij k sigma k. The last term of the epsilon vanishes, however, because the sigma is antisymmetric and xi xj is symmetric. And xi xj into the Kronecker delta just gives us R squared, so we get R squared over 4. That is then multiplied by 3. So this first term here becomes 3/4 R squared. On the other hand, the operator S squared is equal to 3/4, because that's times S plus 1. So the last term is minus 3/4 R squared. Can you see that? And the result is this whole ugly expression goes away also. And all that's left is the L squared over R cubed. So after this work on job we just did, what we find is that J dotted into G is equal to L squared over R cubed. All right. So if we can still see here, what's going to go into this matrix element is I dotted into, not G, but I dotted into J. There's a constant JJ plus 1 we can take out outside the matrix element. And then J dotted into G just became L over R cubed. So if I put that all together, what I get is delta E is equal to K divided by JJ plus 1, taking the constants out. The vectors of the matrix element. Then I've got I dotted into J. And then I've got L squared over R cubed. And then I've got NLJ F M sub F on the right hand side as well. All right, simplification. Now, what about the I dot J? For the I dot J, we use the fact that F is equal to I plus J. And if you square it, you get cross terms, I dot J, which you can solve for. So that I dot J turns into 1/2 of F squared minus I squared minus J squared. Same trick we used earlier in connection with fine structure. So this I dot J then is going to get replaced by 1/2 of the quantity F times F plus 1 minus J times J plus 1 minus I times I plus 1. All right, and that's a C number and then can be taken out over here, out of the matrix element. What's left over is L squared over R cubed. Well, the L squared is easy. It's acting on an eigenstate of itself, so it turns into L times L plus 1. And finally, what's left over then is just the expectation value of R cubed, 1 over R cubed. Well, we saw that before. We did it in the homework, and we used it also in the fine structure calculation. Here to remind you is what it is. 1 over R cubed, this is for Z equals 1, is given by 1 over N cubed times L plus 1/2 times L plus 1. This L and L plus 1 in the denominator are going to cancel out the L plus 1 in the numerator here. So this is just algebra. There's a lot of algebra here. And when the smoke clears, what we're going to end up with is this. We're going to end up in the energy shift is equal to our constant K, which I'll now write out explicitly as GE times Bohr magneton times G nuclear times nuclear magneton. And then we get, let's see if I can get this right. Then we get F times F plus 1 in the numerator minus J times J plus 1 minus I times I plus 1 divided by N cubed. And then we get J times J plus 1. And then we get 2L plus 1. So there is the result. There's the energy shifts. So that is the calculation of the hyperfine energy shifts by degenerate perturbation theory, using only the magnetic dipole field of the nucleus. It's amazing you can do such a thing. This is Fermi's result. Now this is written in atomic units. If you want to put it into ordinary units, one can observe that the G factors, of course, are dimensionless, and the mu's are both magnetons, or they're units of magnetic moment. Magnetic moment squared divided by the Bohr radius cubed as dimensions of energy. And since the Bohr radius is equal to 1 in atomic units, I can put in an A0 cubed here without changing the value. But the result is I now have something which has dimensions of energy in Gaussian units, and so the result is now correct in Gaussian units. This is all quantum numbers here. Okay, so what does this tell us? This applies for the case of hydrogen. It tells us that including the hyperfine effects, you see the energy levels depend not only on N, L, and J, which they did already with the inclusion of the Lamb shift, they did already, N, L, and J, but they now also depend on the quantum number F. So the energy eigenstates have the quantum numbers N, L, J, F, and M sub F. And what we see is that including Lamb shift and hyperfine effects, we see that the energy levels depend on all the quantum numbers except the magnetic quantum number. And this is the generic situation which applies in systems with rotational invariance. You get degeneracy in magnetic quantum number for the total rotations total angular momentum because of rotational invariance, but there's nothing else. There's no additional symmetry. All the extra symmetry has now been broken by all the extra effects that we've added here. Now then, but the energy levels now depend on the quantum number F, which is the quantum number of the total angular momentum. In the case of hydrogen, hydrogen is the most important example of this. No, I shouldn't say that. Hydrogen is an important example of hyperfine effects. I'll say something about other examples in a minute. Hydrogen is an important example of hyperfine effects. And in hydrogen, the most important case is the ground state. The ground state, of course, is the 1s 1/2 state in the usual designation for hyperfine quantum numbers. This means J is equal to 1/2. Of course, the L value is equal to 0. That's what the S means. So it's L. So the electronic angular momentum is really purely spin. It's really S equals 1/2. The J comes purely from spin, and there's no orbital contribution. The nuclear spin, of course, is I is equal to 1/2. So combining the J with the I to give us an F, you see, it's really just combining the two spins, the electron spin and the nuclear spin. It's going to give us F is either equal to 0 or 1. We get singlet or triplet states, combining the two spins. The singlet state F equals 0 is the lower state. You can see from the formula that the energy is an increasing function of F. So the 1s 1/2 state splits under hyperfine effects into an F equals 0 lower state and an F equals 1 upper state. And the lower state F equals 0 is non-degenerate. It's got a degeneracy of 1, whereas the upper state is threefold degenerate because there's 3 magnetic quantum numbers and F equals 1. This means that the true ground state of hydrogen, including all the hydrogen with a proton as a nucleus, including all the physical effects, is really a 0 angular momentum state. It's a rotationally invariant state, but you have to include the nucleus as well to see that, because with the 1s 1/2, you've got a non-vanishing spin, you see, in the ground state. All right. So these two levels are split by a certain energy, delta E. And this energy is much, much less than the separation between the 1s and the n equals 2 levels. They're so far away they can be ignored for the sake of this discussion of what happens to the ground state of hydrogen. Basically, it splits into two states. This separation is in the microwave range of frequencies. It's about 1.4 gigahertz. If I put it in, I think it's 1.4. Let me write it more clearly. I believe it's 1.4 gigahertz. You can check the exact number on this. Is the splitting. So this is way below optical frequencies, and it's also much smaller than fine structure. The fine structure for the n equals 2 levels would be 10 gigahertz, and this is an S level, which has a larger effect. All right. Anyway, that's what it is. That's what it is numerically. If you put this into wavelength units, it turns into 21 centimeters is the wavelength of the photon that's emitted and making a transition from F equals 1 to F equals 0. This photon, this 21 centimeter photon, is quite important in astrophysics. I shouldn't need to say this, but we're talking here about atomic hydrogen and not molecular hydrogen. So you wouldn't see this with a bottle of hydrogen gas in the laboratory, which is all molecular hydrogen. But out in space, the clouds of hydrogen which exist out there, and there are big ones with large masses of mostly hydrogen in them. These clouds, depending on circumstances, may be at such a low density that the hydrogen is split into hydrogen atoms rather than hydrogen molecules. I hope you know from your stat mech course that as you increase the volume, it's entropically favorable to split apart molecules. They break up into atoms. So in fact, there are large clouds in galaxies, including the Milky Way galaxy, of atomic hydrogen. And these clouds are maintained by the way, this 21 centimeters or 1.4 gigahertz, if I turn it into temperature units, it's some fraction of a Kelvin. I forget the exact number. It's less than 1 Kelvin. The actual temperature of these clouds is considerably higher than that. It's in the 20 Kelvin, something like that. You know, very cold by ordinary standards, but still much higher than the energy separation between the two. And what that means is that at that temperature, the populations of these two levels is determined mainly by the degeneracy, because the Boltzmann factors are almost the same. So that would be a 3-to-1 ratio of population of the upper and the lower states. So what that means is that these atoms, the atoms that are in the upper states are free to emit a photon and drop into the lower state. The photon has this wavelength of 21 centimeters. And thus these clouds of atomic hydrogen, which are out there, radiate at that wavelength. Now, you wouldn't need me to be telling you this if you had seen the movie Contact with Jodie Foster, which came out about, now it's almost 30 years ago. The movie is really quite dated nowadays. In case you see it, it's really kind of pretty hard to watch, I think. But this is the one where the aliens communicate with us on 21 centimeters because they know we'd be listening. Actually, they don't. They do it on the double frequency. They do a harmonic of 21 centimeters, and they start sending prime numbers, you know, so we know it's not random. Anyway, the 21 centimeter radio line is important in radio astronomy for many purposes. For example, it was used originally to the original demonstration that the Milky Way is a spiral galaxy came from observation of these clouds and the Doppler shifts in this radio line. Okay, so that's one application of hyperfine effects. Another one is to atomic clocks. Atomic clocks don't work with hydrogen, although atomic clocks can be built on hydrogen, but they normally aren't. Atomic clocks are normally built on cesium, at least this type of atomic clock is. Cesium, so is it 133 cesium is the isotope they use. It has a nuclear spin I equals to 7/2. And if you combine that with the electron spin of 1/2, what you get is a total spin F, which is either equal to 3 or F equals to 4. And so the hyperfine structure of atomic cesium in the ground state is split into two F values of F equals 3 and F equals 4. And the transition between these two hyperfine levels is the basic oscillator, which is used in establishing the cesium clock. Cesium atomic clock actually works by having a resonant cavity that's oscillating at close to this frequency, combined with two Stern-Gerlach apparatuses, one coming before and one coming afterwards. And what they're used for is to detect whether or not the spin flip has been induced by an RF frequency, which is near this transition frequency. If it starts to drift away so that it's getting off resonance, what happens is that the transitions don't take place. The beam that comes out of the second Stern-Gerlach apparatus doesn't end up at the right place. A counter which counts impacts of cesium atom starts to say, oops, the beam is starting to move away. We need to readjust the frequency. There's a feedback circuit that goes back and then changes the frequency of the oscillator so it stays locked on the frequency of the transition. That's roughly how it works. It's like an op-amp. It's got a feedback mechanism. All right.
Sorry, just a question on the 21 centimeter line. So do the contact terms not make that much of a difference, because these energy shifts are only true for L not equal to 0?
Oh yeah, thank you. That's a very good question. You're reminding me that I meant to say something. I did the calculation for the case L not equal to 0. However, it turns out if you do the calculation for L equals to 0, you get the same answer. In fact, that's part of the homework this week. You'll see how it works out. It's not that hard to do the homework, actually. But yeah, thank you for bringing that up, because that's an important point. The formula is actually the same for L equals to 0, and you're quite right. What I just did wouldn't work for the ground state of hydrogen. Very observant. Okay, so that's mostly what I want to say about atomic structure, hydrogen. A lot on hydrogen. I hope you're impressed with how much physics there is in hydrogen. I certainly was the first time I went through this. It's really a beautiful story, I think. it's also not the end of it, because the lamb shift involves a whole new set of considerations. We may take that up next semester. It depends on how the semester goes. So are there any questions about otherwise I'm done with hyperfine effects. Are there any questions about hyperfine effects? Are there any questions about anything else from atomic structure, which has been the topic of the last several lectures? Well, if not, then we're through with the material that I wanted to cover for the semester. No intention of going beyond this. If there's, I'll give you a chance for more questions, and if that's done, we can call it quits for the evening.
Yeah, I had a small brief question. Could you go back to the previous page?
I'll try to. Let's see here. I think it was running through the algebra. Was this the previous page?
Could I see the top? I think that was the one. Yeah. Just the top edge. Yeah.
That came down from the previous diagram like this.
Oh yeah, thank you. So when we evaluate the, when we're trying to rewrite the I dot G.
Yes.
Then I understand that, like, it seems like the G can be replaced using like the Dirac's commutation.
Yeah, it's
like
a projection. It's called the projection theorem.
Projection theorem, yeah. So that seems to make sense for if it was just a matrix element of like G and then just sandwiched by the kets, but then
yeah, if it were sandwiched by J eigenstates like J and M sub J, that's what you're thinking, right?
Yeah.
No, you're quite right. So the way to really justify this is you'd need to do the Clebsch-Gordon expansion to expand that out, you see, as linear combinations of products where you really would have the JMJ, but it wouldn't change anything because this substitution would work for all of those terms.
Okay. Oh yeah. Oh, there's no MJ in this. Okay.
Yeah. So no, but you're quite right, and I appreciate you the detail of that you're noticing on this calculation. I did indeed gloss over that.
And also the fact that it's I dot G, it seems like we can't pull out I just directly from the sandwich.
Well, no, because it's an operator.
Right. So then I guess how do we just replace G with the stuff in terms of J and J dot G?
Well, G is a purely electronic operator, and J is the total electronic angular momentum.
Because when we did
if you wanted to, I could insert a resolution of the identity between the I and the G, and then you'd have nothing but J states sandwiching around the G part. If that would help your analysis.
Oh, okay, I see. Oh yeah, okay, maybe that makes sense. Yeah. All right, thank you.
Yeah, no, indeed. I've glossed. I have indeed done what I try not to do, which is to hand wave over some things. But that's indeed things that one can think through here. Be careful about this. All right. Are there any other questions? Okay, well then that's the end of this lecture. So to remind you, in case you didn't see the email that I sent out, I will be having office hours tomorrow. The homework isn't due tomorrow. It's not due until next Thursday, but it's a long homework, and you have more than a week to do it. I think it's almost 10 days. But my advice is to work on it tomorrow enough so that you got some questions, and so you can make use of office hours. Of course, the GSI has office hours too tomorrow. Okay.
Will you have office hours next week?
Yes, I will. And I sent out an email about that. So check the email. If you have any questions, you can write me an email. I'm planning on having office hours next Thursday because the homework is due on Thursday. I know it's an odd day, but the reason it's due on Thursday is because I need to give time for the readers to be able to grade the homeworks before the final exam. And that's what that date came from them. They said, we need this time. So that's it.
Are you going to have any office hours after the homework is due?
You mean like with homework's due on Thursday, would I have office hours next Friday?
Or like, oh, well, I think the exam is on Thursday, but like before the
Oh,
exam.
yeah, before the exam. Yeah, I can do that. I can do that. Maybe Friday's too early. Maybe like into Monday or Tuesday would be better.
Mhm.
Yeah, I can do that.
Okay,
Let me think about what's a good day for it.
okay, thank
Maybe
you.
Maybe Tuesday's a good day. It's, end of the week.
Yeah, sweet, thanks.
Sure. Okay, anything else?
I have a question.
Yes.
For the final exam, do we can have two papers that write some formulas in the exam?
Yeah, so that's what they call a cheat sheet.
Yeah.
You know this expression? Yeah,
Uh,
no, it will be a closed book exam. So that means that I'll supply you with any extra material you need. Like I'll certainly give you Clebsch-Gordon coefficients or other, if it's other complicated stuff, I'll give you that.
oh, okay, thank you.
I promise you, I'll give you a Clebsch-Gordon table of Clebsch-Gordon coefficients. And I haven't written the exam yet, so I don't know what else is going to be there. Okay, any other questions? Okay, I kind of don't like cheat sheets because some people, spend hours writing down little tiny letters, every formula in the book, and it's okay to write stuff down to review it, but I hate to see a competition between who can write the tiniest letters and stuff.
Yeah, because I think maybe some formula like the orthogonal relationship for the homeotic functions or some spatial functions, I think it's hard just to remember them. But if you
Well, orthonormality
can look at
relations
them, it's
are
easy to
easy. Orthonormality
solution.
relations are easy because they're delta
I
height.
mean, you just some spatial functions that maybe it's
Yeah, no,
a little.
I won't expect you to remember hydrogen atom wave functions. Don't worry about that.
Oh, okay, thank you.
So if you want to know what you need to remember, think about stuff that's been used over and over again in the course. Okay. Okay, if that's all, then we'll call it an evening. By the way, I lost the video from Tuesday night because I clicked the start record button instead of the stop record button, and it completely erased the 2 hours of recording. So now I know what to do. So here we go. We'll pause the recording.